So you can show that the most general solution, which is asymptotically ADS3, can be written in the following form. So this, in terms of these, so it's these, you're looking for SL2R gauge fields which satisfy this equation. And so in this explicit basis, L0, L1, L minus 1, it is convenient to take out the radial dependence in this way, and then the two remaining functions, A and A bar, you can show using the equations, the flat connection equations, that they must they take this form, but these are arbitrary functions. So these are completely undetermined by the so the phase space of all solutions is parameterized by these two functions, L of W and L bar of W bar. So
excuse me. Yeah. Why this guy does not depend on L0?
So you've taken out the L0 piece in this. So you have to. This is I've not showed this to you, but you have to show that if I take out if I parameterize my gauge field in this way with the radial dependence, this taken out, then the remaining equations of motion for F equal to 0 and F bar equal to 0 are satisfied. So they become equations for this A and A bar, and you can show that the most general solution to those equations is of this form. So that's a result of a calculation.
Sorry, but you're saying that is an artifact of a gauge choice. Is that?
No, this is a particular convenient parameterization of the solutions. This will be directly related to, yeah, of course, by making gauge choices, you can always put back in L0 and whatever. But this is a
I kind of thought that this must be some boundary condition requirement because when you
there is a boundary condition, so that's why there is an asymptotically ADS. So let me write down the ADS solution in these coordinates, the global ADS solution, and then you will see that these are so that global ADS corresponds to a particular value of L and L bar, and so that's what makes this this thing. In fact, yeah, maybe since if you now use this B and B bar, B to sort of go to the A and A tilde, the original A and A tilde, they take the following form: e to the rho L1 So if I write, sorry, this is the dW. dW bar. So you get A and A tilde can be written in terms of, so the explicit form for A and A tilde, the full radial dependence is like this. So here, of course, there is a L0 when you and this thing. Now you can ask what kind of metrics these correspond to, because once you have these this form of A and A tilde, you can read off your E, your field bind. The field bind is just the the EA is just the difference of A and A tilde, and once you know the field bind, you can read off the metric because G mu nu is basically E mu A, E mu A. So so G mu nu, which you can write as sort of trace of E mu E nu, because the contraction of the indices is essentially the trace, and the SL2 are so 2, 1. So this and E mu and E nu you read off from the gauge field, from the A and A tilde, and when you do that, you find that ds square. So this implies that the metric ds square is equal to d rho square plus so if you take this form of A and A tilde and write out the metric, it looks like this. So what have we done? We have looked at sort of the most general solution of this flat connection and written it in terms of this was parameterized by these L and L bar, and we have written out the metric corresponding to that. So there's a d rho square, and that's the radial part, and then the W and W bar, you remember, are just the phi and t. So you get this. So by the way, I should say that right now I've gone to the Euclidean picture because we can always look at the Minkowskian signature by a Wick rotation, but it's convenient to talk at this stage the Euclidean picture. And in fact, these are what are called the Pfefferman-Graham coordinates of for ADS. Pfefferman and Graham showed that you can sort of write any asymptotically ADS, any hyperbolic metric in terms of a convenient set of coordinates, and these are the Pfefferman-Graham coordinates precisely. So this construction, so this parametrization was designed to sort of reproduce this, give you this Pfefferman-Graham coordinates, and in terms of this. The BTZ black hole corresponds to L equal to and L bar equal to so this is the so-called mass angular momentum of this. So so in these Pfefferman-Graham coordinates, which is a way of characterizing any asymptotically ADS metric. You have this mass and angular momentum. These are just L and L bar. That's a special case of this, where L and L bar are just constants, which depend on which you can parameterize. So two constants, so you can parameterize these two constants in terms of two other numbers, m and j, which turn out to be the mass and angular momentum of the BTZ metric, the BTZ solution. And global ADS is a particular instance of the BTZ family. It has m equal to minus 1 over 8 g Newton, and of course it has no rotation, spherically symmetric, so j is equal to 0. Yeah. So this is the so this family contains within it global ADS solutions and as well as the BTZ black holes, but it has a more general class, which is this L and L bar, and for those who know a little bit of ADS CFT, this L and L bar correspond to the boundary value of the stress tensor. Which you can see from this Pfefferman-Graham expansion that there's a particular subleading term in the metric, which is, so this Pfefferman-Graham expansion is designed so that you have a leading piece, which is the ADS, and then the subleading pieces, which correspond then to the stress tensor on the boundary. So these are this L and L bar, both correspond to this holomorphic and anti-holomorphic stress tensor, which is a signature that you have a sort of a CFT, and these are the corresponding stress tensors. Okay, any questions about this? So this is how in the frame formulation you sort of recast some of the familiar objects of 3D gravity. Yeah.
For BTZ black hole, does one have to introduce periodicity in timer?
Yeah, so if you are in the Euclidean, yes. So in fact, that's a good question. I should just mention that. So what is being referred to is the fact that when you're a Euclidean solution, then there is the Euclidean black hole solutions have a time direction which is now compact and has a certain periodicity which is identified with the inverse of the temperature, and usually that temperature is fixed in terms of the mass and the angular momentum. By the so-called Gibbons-Hawking procedure, which tells you that the size of the circle is fixed by the periodicity of the circle is fixed by requiring that at the horizon there's no conical singularity; it smoothly sort of shrinks to 0. And so that's how you would, in the metric formulation, try to identify the periodicity of the solution. So you can ask what is the corresponding statement in this frame language, and that will be very important when you generalize to higher spin theories, because there this metric picture will not be present, and so it will not be clear what corresponds to this regularity at the horizon. So there's a nice geometric criterion which plays the role of regularity. So let me just mention that. And so there is an identification of the time direction which is usually fixed by the Gibbons-Hawking procedure. So you can take this metric and demand that, so this W and W bar, remember W was like phi plus IT, so if, so it's a complex coordinate, but now phi was of course periodic, so phi was periodic, let's say 2 pi, but time also, if it is periodic, then essentially you have two periodicities, so it's like a parallelogram, so this is the geometric depiction of a torus with sort of modulus tau. You can fix this periodicity in terms of this original metric by this Gibbons-Hawking procedure that I just mentioned about requiring regularity. But in this frame formulation, there's an alternate way to arrive at this. So in the frame or Chern-Simons formulation, there's a beautiful prescription, which is that, so since f is equal to 0, there are no local gauge invariant observables in the theory, but there is a global observable which cropped up in the last lecture also, which is the holonomy. So you can consider the holonomy of this gauge field A around this time-like direction, so this is a non-contractible direction, this is a non-contractible direction, but these are both on the boundary, they are non-contractible directions which form a torus, but the Gibbons-Hawking calculation was telling you that this is shrinking to 0 at the horizon, and that was the given, and you require it to be non-singular, and so if tau is sort of the periodicity along the time direction, so the Gibbons-Hawking procedures told you this was shrinking smoothly to 0. But now you can talk about the holonomy of these gauge fields along this time direction, so the holonomy is the path-ordered exponential of A or A tilde, so along, say, this time direction t, this time circle, or this circle here. So you can look at this matrix. Its eigenvalues are gauge invariant by construction. That's what the path-ordered exponential does for you. In fact, you normally take the trace to define, say, the Wilson loop, but you can look at all the eigenvalues. They are also gauge invariant. So this holonomy must be trivial. So the criterion in this frame language or Chern-Simons language is that this holonomy must be trivial along this cycle because it is a contractible cycle. So if you the condition that there's no singularity is equivalent to the statement that this holonomy because you can this holonomy, because the field strength is 0, is independent of where you are. So in particular for a tiny loop, it should be the same. So if it is smoothly contractible, that must be telling you that this holonomy must be trivial. So trivial means that it is in the center of the gauge group. That means it is an element of the gauge group that acts trivially. So usually you think of that as the identity element, but it's actually slightly larger. You can have the so-called center of the gauge group, in which whose elements act trivially. So in the case of SL2R, the center is center is Z2. So basically you have the identity and minus the identity. So these two are the elements of the center which act non-trivially. These are the two elements of SL2R which act trivially. So this holonomy must be one of these, and in fact it turns out that it should be sort of equivalent to this, that namely by diagonalization its eigenvalue should be -1 and -1, and not this. This is essentially because you, when you have a time-like direction, the fermions should be anti-periodic when you go around the time direction, and that's what in fact this -1 reflects the parallel transport, the phase factor that you get when you transport a fermion or a spinner under the SL2R around this circle. So this is the criterion that this path-ordered exponent should have eigenvalues which are -1 and -1. And in fact, you can work that out for this connection for the BTZ black hole with L and L bar. You can see what the eigenvalues are. So basically, I just take the eigen. So this is basically like e to the 2 pi times tau times a of z, and you can write a similar one for a as well as a tilde. So you get these two matrices because the A is essentially conjugate to capital A is conjugate to little a, and capital A tilde to little a tilde. And if you have a time direction tau, then you basically get these, and you can, knowing the explicit form of A and A bar, you can diagonalize these matrices. Remember, I gave you the 2 by 2 form for L and L plus minus 1, so you find that the eigenvalues are e to the plus minus square root 8 pi cubed so if you demand that this is equal to e to the plus minus I pi, for this to be true, then this implies that tau, you fix tau, and similarly tau bar to be equal to, so these are these k hats that were there in the Chern-Simons. So this k should be really k hat. So you find that tau is fixed. Demanding this, you get tau is something ik over 2 into 1 over 2 pi k L hat. And this is indeed the sort of periodicity. So tau, you take the imaginary part of tau, that gives you the beta in the time periodicity. So this you can check is what you would have gotten from the Gibbons-Hawking procedure. So this prescription about requiring the holonomy to be in the center of the gauge group is equivalent to the Gibbons-Hawking procedure, but it's a gauge. So we have the whole goal is to reformulate many of the intuition and the features in the usual metric-like formulation into this gauge theory language, because when we generalize to higher spins, we won't have the metric-like intuition will not be there. So it's more useful to think in terms of the gauge theory intuition. So that's why for these black hole-like solutions, it's useful to view them in this way. And this will enable us to find new black holes in the higher spin theory, new black hole solutions in the higher spin theory. So, okay, so this is sort of what I wanted to say about the higher spin, about the Chern-Simons formulation of gravity, but okay, maybe I should. In the remaining 5 minutes, I'll just start by introducing the higher spin, the formulation of higher spin theories in this language. So, so I'll make the statements and then maybe start justify them more fully next time. So. So here we had so gravity. The bottom line was we reformulated it in terms of two copies of Chern-Simons theory, the two SL2R gauge fields A and A tilde. And so if you generalize that to SLNR, n is an integer greater than 2. So this corresponds to the SLNR times the SLNR generalization. So basically that's why I did this SL2R case in detail. Now you just promote all the A and A tildes to SLNR matrices, n by n matrices. Then I claim that that corresponds to a higher spin theory with interacting. So it's an interacting higher spin theory with interacting higher spin gauge fields, massless fields of spin s equal to 2, 3, all the integers up to n. So n equal to 2, of course, is the case where it's just 2, but I claim that if you consider the n by n case, so this is A tilde, so our n by n SLNR matrices. SLNR matrices is basically n by n real matrices with determinant equal to 1. And so the gauge fields are in the SLNR are in the Lie algebra, so they're traceless n by n matrices. Gravity and the S equal to 2 field